Welcome to the Deep Dive, where we unpack complex topics and distill them into essential, actionable knowledge. Today, we're plunging into a world where the stakes are incredibly high, and the adversaries, well, they're constantly adapting. We're talking about the cutting edge of comprehensive fraud detection in digital platforms. Think about it. Every time you buy something online, log into an account, maybe sign up for a new service, behind the scenes, there are these sophisticated systems working tirelessly to protect you and also the platforms you use. But what makes this fight against digital deception so incredibly challenging is not just, finding the bad actors. It's about doing it at lightning speed, often with imperfect information and against an enemy that's always changing its playbook.
It truly is a dynamic battlefield, constantly evolving. We'll explore the foundational challenges that make digital fraud detection so unique, things like the inherent rarity of fraud itself, which is a huge one, to the clever, almost chameleon-like ways fraudsters try to hide in plain sight.
Right. And we'll unpack the advanced techniques used to combat them. We're talking cutting-edge feature engineering, powerful machine learning models that don't just predict but also learn and adapt, and some really ingenious strategies to ensure these complex systems don't just work, but work fast, fairly, and continuously. Our mission today is to basically give you a shortcut to being truly well-informed on this critical area. Drawing straight from the sources we've meticulously explored, you'll gain, hopefully, a deep understanding of the subtle signals of deception, the intricate systems designed to catch them, and the ongoing high-stakes game of digital cat and mouse.
Yeah, we've gathered insights from various expert materials on the subject, almost like assembling a detailed, multi-layered map of this complex landscape. We'll guide you through each layer of defense, showing you not just what is done, but also why it's done that specific way.
Okay, let's unpack this. When most people think about a fraud detection system, they might imagine, I don't know, a simple on-off switch. Is it fraud or isn't it? But from what I understand, it's far more nuanced and, frankly, way more difficult than that. What are the fundamental hurdles that make comprehensive fraud detection so incredibly difficult for digital platforms?
You've absolutely hit the nail on the head there. It's anything but simple. At its heart, fraud detection really sits at the intersection of several profoundly challenging areas in, well, data science and operations. We're talking about things like class imbalance, which is a big one we'll start with. Then there's adversarial behavior, the fact that fraudsters fight back. Also, ambiguous supervision, meaning we don't always know for sure what is fraud. And finally, the very real challenge of business risk tied to every single decision the system makes. So let's start with the first one, class imbalance. We often call this the needle in the haystack problem. And here's the counterintuitive truth about fraud detection. Success isn't about being right 99% of the time overall. It's about building a system that specifically targets and learns from that microscopic fraction of activity, like way less than 1% sometimes, that actually represents fraud.
Wow, that's a tiny sliver of data to work with. I can immediately see why that's a challenge.
Yeah.
If a system is just trying to be accurate in the traditional sense, it could completely miss the point, right? How does that rarity uniquely challenge the machine learning models?
It fundamentally changes how you measure success, how you even think about building the model. Consider this. In many digital platforms, less than 1%, and sometimes, like I said, even as low as 0.1% of all transactions are actually fraudulent. Now, imagine a machine learning model. If it simply predicted not fraud for every single transaction every single time, it would still achieve, let's say, 99.9% accuracy or even higher.
Which sounds great on paper.
Exactly. It sounds fantastic. But that model would be completely useless to a business because it would catch absolutely zero fraud. Traditional accuracy metrics are deeply misleading in this context because they heavily favor the dominant not fraud class. They just get overwhelmed by the sheer volume of legitimate activity. Let's take an example. Think about a popular food delivery app. On a busy Friday night, maybe it processes 1,000 transactions, but let's say only 50 of those are actually fraudulent. Someone using a stolen code, maybe creating fake accounts for promo abuse. Now, your fancy new fraud model comes along. It analyzes all 1,000 transactions and predicts that 70 of them look fraudulent. Okay. Now, out of those 70 flags, it turns out 40 were correct. You caught 40 actual frauds. That's good.
Already 50 caught seems decent.
Right. But the model also wrongly flagged 30 legitimate transactions as fraud. Those are what we call false positives. So 30 real customers suddenly get their dinner order canceled. Maybe their account gets temporarily frozen. That's a bad experience.
Yeah, that's terrible for the customer.
And crucially, the model missed 10 actual fraudulent transactions. It incorrectly labeled those as legitimate. Those are false negatives. The company still loses money on those 10 missed frauds. So if you just look at the overall accuracy, maybe it's still 99% correct because it got most of the 950 legitimate ones right. But it's incredibly hard to tell from that single number how well it's actually doing on the specific task of catching fraud without massively inconveniencing your good customers.
Okay, so it's not about being right generally, but about being laser-focused on being right on those specific rare instances that actually matter most. That's a critical distinction. How do we address this then if overall accuracy isn't the right yardstick?
Precisely. To truly get a handle on this, we have to shift our focus entirely. We prioritize metrics that actually reflect performance on that tiny minority class, the fraud class. We look closely at precision and recall. Precision basically asks, when my model says this transaction is fraud, how often is it actually right? Think of it like a fraud analyst being very careful with their red fraud stamp. High precision means fewer legitimate customers are falsely accused and blocked. In our food delivery example, with 40 true positives caught but 30 false positives also flagged, the precision would be 40 divided by the total flagged. 70, which is about 57%. So you're pretty good when you stamp fraud, but you're definitely making some costly mistakes too.
Okay, so precision is about the accuracy of the fraud flags themselves. What about recall?
Right. Then there's recall, which asks the opposite question. Out of all the actual fraud that happened, how much of it did my model successfully catch? This is more like casting a wide net to catch fraudsters. High recall means you're not letting much actual fraud slip through unnoticed. In our example, we caught 40 true positives, but we missed 10 actual frauds, the false negatives. So the recall would be 40 divided by the total actual frauds, 50, which is 80%. So your net caught most of the fraudulent fish, but some definitely slipped away. Finding the right balance between precision and recall is always this delicate dance. You often have to trade one off against the other. That's why we frequently use metrics like PRAUC, which stands for the precision recall area under the curve. It's particularly vital for these highly imbalanced problems because it measures the model's ability to maintain a good balance between precision and recall across various decision thresholds.
So PREUC gives a more holistic view of that trade-off.
Exactly. And beyond just the metrics, we use specific techniques during model training. Things like class weighting, where you basically tell the model that misclassifying a fraud instance is, say, 100 times worse than misclassifying a legitimate one, or various sampling strategies. Like you might do undersampling, where you just randomly remove some of the overwhelmingly large number of not fraud examples to make the data set look more balanced. Or you might use oversampling, perhaps with a technique like SMOTY, which stands for Synthetic Minority Oversampling Technique.
SMOTY, how does that work?
Yeah, SMOTY is pretty clever. Instead of just duplicating the few fraud examples you have, it actually creates new synthetic fraud examples. It does this by looking at existing fraud cases and creating new data points that are kind of like them, but slightly different, basically interpolating between nearby fraud examples in the feature space. It's like drawing new dots around the original fraud clusters to give the model more examples of what fraud looks like to learn from without just repeating the same ones over and over.
Huh. Interesting. So essentially, we're explicitly teaching the model that missing a fraud is a much bigger deal than a false alarm, forcing it to prioritize catching those rare events. But even if we get that right, aren't the fraudsters themselves constantly changing their tactics, making our needle look completely different next week? This really sounds like a never-ending game of cat and mouse.
It absolutely is. And that brings us neatly to the second core challenge: adversarial behavior and concept drift. Fraudsters aren't static targets, not at all. They are active, cost-sensitive adversaries. They're constantly probing systems, testing defenses, adapting their tactics, and actively trying to mimic normal user behavior specifically to avoid detection. This dynamic nature is precisely why we encounter concept drift. Concept drift means that the very definition of fraud, or the patterns and features associated with it, change over time. What worked to detect fraud 6 months ago might be completely ineffective today. An old model quickly becomes obsolete, just like an antivirus program that hasn't had its virus definitions updated in months.
Right, the threat landscape evolves.
Constantly. Imagine you've successfully built a model that blocks transactions originating from a specific range of IP addresses because those IPs were heavily associated with fraud last quarter. What do the fraudsters do? They immediately rotate their IPs. Maybe they invest in sophisticated proxy networks or start using legitimate-looking residential proxies to completely mask their true origin. Or perhaps a completely new type of promo abuse emerges. Maybe fraudsters figure out a way to chain together hundreds of fake referral codes using generated identities to get endless discounts for an elaborate scam. Suddenly, the features that were highly predictive based on past behavior, like number of referrals from this IP, might quickly lose their power because the fundamental attack pattern has shifted entirely. Your model is essentially learning from yesterday's war, but the enemy is already fighting tomorrow's battle.
So it's not just about learning what fraud was, but constantly trying to predict what it will be as it changes in real time. That's quite a dynamic to manage. It implies that these models have a really short shelf life, almost like perishable goods.
Exactly. That's a great way to put it. This directly implies that continuous model retraining and really rigorous monitoring are absolutely crucial. You cannot just build a model, deploy it, and forget about it. You have to be building what we call a living ML system, one that can adapt and evolve alongside the fraudsters. If you don't keep up, your defenses quickly become ineffective. This also ties into related concepts like data drift, where the distribution of your input features changes over time. Maybe users suddenly start using a new type of device, or model drift, which is the resulting degradation in your model's performance. Detecting these shifts, for instance, by continuously comparing the statistical properties of new incoming data against the data the model was trained on, is paramount. It's like a radar system that has to constantly adjust its calibration to detect new types of stealth aircraft that didn't exist when it was first built.
Okay, that makes sense. Now, moving on to the third challenge you mentioned, label ambiguity. This sounds like sometimes we're not even completely sure what is fraud and what isn't. How can a model possibly learn effectively when the ground truth itself is blurry?
That's a really profound point, and it's right at the core of the difficulty. It's often incredibly difficult, sometimes impossible, to know if a given transaction was truly fraudulent with 100% certainty. And this inherent imperfection feeds directly back into the data we use to train our models. The labels we use, the tags saying fraud or not fraud, they come from various sources, and each source has its own limitations and imperfections. For example, probably the most definitive indicator of payment fraud is a chargeback from a credit card company. That's when the legitimate cardholder disputes the charge.
Right, that seems pretty clear-cut.
It is, eventually, but chargebacks are often significantly delayed. They might arrive weeks, sometimes even months, after the original transaction occurred. This makes using them for real-time learning incredibly difficult. By the time you know for sure that transaction was fraud, the fraudster might have already hit you dozens more times. Then you have manual reviews conducted by human analysts. While these are invaluable for catching nuanced fraud, they can be inconsistent. One analyst might be more conservative or more experienced than another. They might be under immense time pressure to clear a backlog, leading to subjective judgments or mistakes. And finally, you have signals like customer complaints. These can be valuable indicators of potential issues, like someone complaining their account was hacked. But they can also be subjective, sometimes exaggerated, or even misused by so-called friendly fraudsters who engage in refund abuse by falsely claiming items didn't arrive or were defective just to get free stuff.
Wow, so it sounds like many true frauds might just slip through the cracks and never get labeled correctly. And conversely, some legitimate transactions might get wrongly flagged, maybe investigated and then cleared, but still create noise in the data the model learns from. How does a model cope with learning from this kind of imperfect reality?
Precisely. And the reason this matters so much is significant. Many frauds simply go undetected, especially more subtle types like policy abuse or account takeovers that don't result in immediate chargebacks. This leads to false negatives being present in our training data, actual instances of fraud that were never flagged or confirmed as such. Conversely, as you said, some legitimate transactions might be wrongly flagged, reviewed by an analyst, and then correctly cleared. But if that initial incorrect flag somehow makes it into the training data pipeline, it creates noise. The implication here is that our models are fundamentally learning from an imperfect, noisy ground truth. This really emphasizes the need for model robustness. We need models that don't just memorize the training data, including its flaws, but can generalize well despite the noise. It means we have to be careful about overfitting to potentially faulty labels. It also highlights the critical role of incorporating continuous feedback loops with human analysts. Allowing analysts to correct labels, provide reasons for their decisions, and essentially refine the training data over time becomes essential for helping the system learn more accurately. It's like the analysts are constantly correcting the model's understanding of reality.
That's fascinating. So the models have to learn from a somewhat blurry picture, which makes robustness and that human feedback loop really key. But then, beyond all these technical data challenges, there's the very tangible impact on the business itself. What about the fourth challenge you mentioned, business risk. This seems to bring the whole technical problem right into the realm of real-world dollars and cents.
This is absolutely where the rubber meets the road. Because unlike many other machine learning problems, say recommending a movie, misclassifications, and fraud detection have significant, immediate, and quantifiable business costs. We're constantly dealing with the consequences of two types of mistakes, false positives and false negatives, and their costs are almost never equal. In fact, they can be wildly different.
Okay, remind us, false positive is blocking a good customer.
Exactly. A false positive, FP, means blocking a legitimate user or transaction. This can lead directly to customer churn. A good, valuable customer gets frustrated because their perfectly valid order gets canceled, or their account gets frozen for no apparent reason. They might complain, they might leave the platform entirely, and maybe never come back. This also generates a wave of support tickets, which cost real money and time to resolve. And most importantly, it results in lost sales from that blocked transaction and potentially the entire lost lifetime value of that customer if they leave permanently. Imagine being a bouncer at a really popular, busy nightclub, turning away a perfectly legal adult who's planning to buy several expensive drinks and maybe bring their friends next week. That costs you tangible, immediate revenue and potentially future revenue, too. It's a frustrating, quantifiable loss.
Right, and the false negative, that's letting a fraudster through.
Correct. A false negative, FN, means failing to detect a fraudster or a fraudulent transaction. This translates directly into immediate and often significant financial consequences. You face chargebacks from credit card companies where the merchant is not only forced to return the money, but often has to pay an additional hefty fee. You suffer losses from refund abuse, where fraudsters repeatedly claim items didn't arrive or were defective. There's the direct monetary loss from stolen goods or services that you can't recover. And potentially, it allows for repeat attacks from the same bad actor, who now knows they've found a vulnerability in your defenses. In our bouncer analogy, letting in an underage person might result in the nightclub getting hit with a hefty $500 fine from the authorities, not to mention severe reputational damage if word gets out. The cost is immediate and often much higher than the cost of mistakenly turning away one legitimate customer.
Okay, it definitely sounds like a very delicate balancing act. You can't just aim for a 100% fraud catch rate if doing so means alienating all your good customers by blocking them too often. The costs seem very different.
Absolutely, and that's the crux of it. The primary goal in operational fraud detection isn't usually to maximize a purely technical metric like accuracy, or even just recall at any cost. The real goal is to minimize the total expected cost to the business. This necessitates a very business-aware approach to building and deploying these models. It requires carefully designing human review workflows for cases that fall into a gray area where the model isn't highly confident either way. This allows a skilled human analyst to intervene and make the final call. It means meticulously tuning the decision thresholds for the model's scores based on their real estimated financial impact. You need to understand that for your specific business, maybe a false negative costs $500 in chargebacks and lost goods, while a false positive costs only $20 in lost margin and potential churn risk. That calculation completely changes where you set the bar for blocking versus allowing. And crucially, it often means ensuring the models themselves are transparent, or at least explainable, so that the decisions they drive can be audited, understood by analysts, and justified to customers or regulators if needed. It's really about operationalizing the model in a way that saves real money and preserves customer trust, not just achieving a high score on some offline evaluation dataset.
Okay, so if fraud is so dynamic and elusive, the data is so imbalanced, and the costs are so tricky to balance, how do we even begin to train a model to reliably spot it? This is where feature engineering comes in, right? It sounds like it's all about turning that raw data into meaningful signals, almost like trying to find the secret language of deception hidden in the noise.
Exactly, you've absolutely got it. Features are precisely how we translate all those complex user behaviors, the subtle relationships between accounts, and the historical patterns we just discussed into something a machine learning model can actually understand and learn from. Think of features as the subtle tells, like in poker, that fraudsters inadvertently leave behind in their digital footprint. Since fraud often reveals itself through inconsistencies, anomalies, unusual speed, or the reuse of resources, creating powerful, well-engineered features is absolutely paramount. It's often said that feature engineering is where most of the magic happens in fraud detection. We typically categorize these features into 5 core types, each giving us a different lens, a different angle to look at potential deception. First, let's talk about behavioral features. These fundamentally ask the question, how is the user acting right now? The core idea here is to capture patterns in the user's interaction with the platform, the speed of their actions, the sequence of steps they take, the rhythm of their clicks. It's really about the flow of their interaction, not just static data points about the transaction itself.
Right, like observing someone playing a video game. Are their moves smooth and natural, or maybe too fast, too robotic? Do they follow the typical patterns of browsing and considering? Or do they just jump straight to the checkout page without looking at anything else?
Precisely that. That's a great analogy. For example, we look at features like the time of day of the transaction. Is it happening at 3 a.m. in a market where most users are asleep? That could be suspicious. We might look at click speed within an application. Is someone filling out complex forms suspiciously fast, maybe suggesting a script or automation is involved? Or we could look at the order time diff between consecutive orders from the same account. Are they placing orders every 30 seconds? That's not normal human behavior. Even the purchase sequence a user follows matters. Do they add items to cart, browse related items, then checkout? Or do they bypass all that? Other really important behavioral features include things like the time from login to checkout, the number of pages visited before checkout, or the average time between user actions during a session. The usefulness here is profound. These features excel at detecting bots, identifying fake urgency, like clicking buy now instantly, or flagging unusual navigation flows that deviate significantly from typical human browsing behavior. Fraudsters using scripts might order at odd hours or make unusually quick checkouts, indicating automation rather than a human carefully considering a purchase. It's all about catching the unnatural rhythm of deception.
So it's about looking at the flow of interaction, not just the static data points. That makes a lot of sense.
Exactly. Building on that, we then move to the second type. Relational features, these answer the critical question: who is connected to whom? The core idea here is to uncover hidden links and shared entities between different accounts, users, devices, or transactions. Fraud, especially organized fraud, is frequently relational and collaborative, often involving sophisticated, interconnected fraud rings.
Ah, okay. This sounds like it moves beyond looking at just one user or one transaction in isolation and starts looking at the broader network view. Like you said earlier, mapping a phone call network between suspects in a crime thriller, or maybe uncovering a massive fraud spiderweb that reveals hidden connections between seemingly unrelated accounts.
Exactly that. This is where we start asking those probing questions like, is this one specific credit card being used by 5 different user accounts, all created within the last week? Is the same single IP address placing orders for 20 distinct users across many different accounts? Are there multiple accounts tied back to the same email address or the same phone number that keep reappearing, perhaps trying to exploit a first-time user promo code repeatedly? Examples of features here include new accounts per card, shared IP count, or detecting email phone reuse across multiple accounts. Other powerful relational features could be the count of other users using the same device fingerprint or IP address, whether this specific card has been seen on another account before, or how many distinct users are linked through a single shipping address. These features are incredibly useful for detecting things like Sybil attacks, that's the technical term, for when a single bad actor creates many fake accounts to overwhelm a system or abuse promotions. They're also great for flagging shared infrastructure like proxy IPs used by multiple fraudsters or reused phone numbers. They expose the underlying structural clues of coordinated fraud rings that looking at individual transaction data might completely miss. It reveals the network.
Got it. So behavioral is how they act now. Relational is who they're connected to. What's next?
Third, we leverage historical features. These address the question, how has this specific user behaved over time? The core idea here is to capture a user's past actions and establish a kind of personal baseline of normal behavior for them. This then allows us to detect significant deviations from their own typical learned patterns.
Okay. So it's about spotting when someone suddenly goes out of character, like reading someone's personal transaction history log or their bank statements to see if this current purchase is normal for them versus a sudden anomalous shift in behavior.
That's the perfect analogy. We look at features like a user's total past order count. Are they a brand new user or a longtime customer? Their historical average refund rate. Do they ask for refunds suspiciously often? Their typical average spend per order, or maybe the time since their last chargeback if they ever had one. You might also track the number of refunds requested in the past 90 days, or their historical transaction variability, for instance, calculating the standard deviation of their past order amounts. Is this purchase wildly outside their usual spending range? The usefulness here is profound. If a user who typically made 30 small, legitimate orders over the past year, maybe averaging $50 on groceries, suddenly places an $800 sushi order to a brand new address using a different payment method than usual, that deviation from their personalized baseline is a very strong fraud signal. These historical features allow for personalized fraud thresholds, making the system much more nuanced. It helps avoid falsely flagging good customers who just happen to be making an unusually large but legitimate purchase.
That personalization seems key. Okay, so we have behavior, relations, history. What's the fourth type?
Our fourth type focuses on device-based features. These explore the question, what technology are they using to connect to us? The focus here is squarely on the characteristics and the apparent authenticity of the device being used for the transaction or login attempt.
Right, essentially confirming the authenticity of the entry point into the system. Like a digital passport check at the border is the same user seemingly logging in from devices physically located in 4 different countries within a single hour. That's physically impossible. Or is this order being placed not from a typical consumer phone or laptop, but from a generic Linux server hosted in a known data center? That's highly suspicious for a consumer purchase.
Precisely. Examples here include capturing the browser fingerprint. This is a kind of unique identifier based on a combination of the user's browser type, version, installed fonts, screen resolution, plugins, and other settings. We also look at the operating system, OS, the device type, mobile, desktop, tablet, or geolocation data derived from the IP address, though this can be easily spoofed. We also look at features like, is this a new device for this user? Has this specific device fingerprint ever been associated with this account before? We track the number of unique devices used by this account in the last 24 hours. Is it suddenly jumping between many devices? And we compare the location distance from the shipping address. Is someone with an IP address geolocated in New York trying to ship an expensive item overnight to Los Angeles using a device that looks like it's in Eastern Europe? These features are crucial for flagging potentially spoofed devices, detecting the use of emulators or virtual machines often employed by fraudsters, or identifying geographic anomalies that might suggest a fraudster is trying to obscure their true origin or is part of a geographically distributed fraud operation.
Makes sense. Checking the digital passport. Okay, one more type left.
Yes. The fifth and final category is aggregate features. These essentially ask, how does this user or this transaction compare to the wider crowd? The core idea here is to aggregate data across various groups, perhaps grouping by IP address, by credit card prefix, BIM, by geographic region, or within specific time windows to identify statistical outliers or sudden unusual spikes in activity that stand out sharply from the established norm for that group.
So this combines individual actions with the broader context of what's considered normal for a larger segment of users or transactions. Like zooming out from the individual user and asking, is this specific behavior extremely rare across our entire user population? Or maybe looking at store-wide sales data for a particular product category, is this customer's transaction amount way, way outside the statistical norm for all customers buying that type of item?
That's exactly it. Common aggregate features include things like the average transaction value seen from this specific IP address across all users, the median value of transactions made with cards starting with the same first 6 digits, the BIN, or the maximum total spend observed in the last 24 hours for a given credit card or user account across all their transactions. We might also compute features like the percent deviation from the average order size within a user's identified behavioral cluster, or compare an IP address's overall average transaction amount versus this specific transactions amount. We could also look at velocity at an aggregate level, like the total number of transactions initiated across all users within the past 5 minutes. A sudden spike might indicate a widespread bot attack. These aggregate features are incredibly useful for detecting things like volume abuse, many small suspicious transactions, velocity attacks, a sudden burst of activity from a single source or against a single target, coordinated promo fraud across many accounts, and general behavioral outliers that might not look suspicious when viewed in isolation at the individual transaction level, but become glaringly obvious when viewed against the backdrop of the larger user base or recent activity patterns.
That's a really comprehensive set of lenses to view the data through. Behavioral, relational, historical, device, and aggregate. It covers a lot of ground.
It does. But what's truly fascinating about all these features, and something that makes fraud detection so particularly challenging and dynamic, is how critical recency is for many of them. Fraud, as we've established, is inherently dynamic. Attackers adapt constantly, often very quickly. Old behavioral patterns, old device associations, old network connections, they often lose their predictive power remarkably quickly.
Yeah, right. So the features themselves are almost like living entities, constantly changing in their relevance and needing frequent updates to stay effective. Almost like a constantly refreshing live intelligence feed rather than a static profile.
Precisely. That's a fantastic way to think about it. Features computed over very recent time windows, like the past 1 hour, the past 24 hours, maybe the last 7 days, are much better at capturing those sudden velocity spikes, identifying the first use of a new device or IP address, and spotting their short-lived burst-held campaigns. This focus on recency is absolutely key because it helps our model stay relevant and effective even between the major retraining cycles, directly addressing that challenge of temporal drift we talked about earlier. Think about it. Knowing that a credit card was used across 10 different accounts last year is interesting historical data. But knowing that the same credit card was used across 10 different accounts in the last hour, that's a far more suspicious and immediately actionable signal, demanding urgent attention. That's why we often talk about needing hot features, features reflecting the immediate past.
Okay, but calculating all these features, especially the complex historical and relational ones, for every user, every hour, or even every few minutes, that sounds computationally very expensive. How do platforms manage that in a live production environment?
You're absolutely right. It is a significant engineering challenge. It leads directly to the need for a tiered feature cache, or what's often called a real-time feature store. The core idea is that not all features need to be refreshed at the exact same rate. You can stratify your approach, balancing the need for freshness with the computational cost. So you might have hot features. These are the ones absolutely critical for making real-time fraud decisions right at the point of checkout or login. Think velocity counts, transaction count last 1 hour, shared IP flags, new Mr. Sonoplast 5 mins, or maybe device foreseen timestamps. For these, you might aim for an update frequency of every 1 to 5 minutes. They need to be stored in ultra-fast, in-memory data stores like Redis or Memcached, specifically designed for lightning-fast lookup with minimal latency. These hot features are crucial for catching bot attacks or rapid-fire card testing fraud as it happens.
Okay, hot features for immediate threats. What about less urgent signals?
Exactly. Then you typically have warm features. These are features that are still important, but perhaps less critical for sub-second decisions. They might be used for things like mid-frequency fraud investigations, populating queues for manual order review, or calculating risk scores that don't need to be instant. Examples could include a user's refund tree at last 30 days, their average order value over the past week, or maybe some graph-based features that take a bit longer to compute. These might tolerate a refresh cycle of 30 to 60 minutes and could be stored in slightly more persistent, but still relatively fast, databases like maybe Redis configured for persistence or DynamoDB.
Got it. Hot, warm, and cold.
And finally, yes, you have cold features. These are features that change very slowly or perhaps are static characteristics of the user or account. Think about a user's accountage, their registered country, their original sign-up channel, or maybe demographic information if available. These might only need to be updated daily, or perhaps they're loaded once and rarely change. They are typically pulled from a large analytical data warehouse like Snowflake, BigQuery, or a Delta Lake during less time-sensitive batch processing or for offline model training. They provide valuable context but aren't needed for millisecond-level decisions.
That tiered approach makes a lot of sense. It seems like a very clever way to balance the need for speed and up-to-date information with the practical realities of computation and cost. But it also sounds like a complex engineering setup to maintain. What's the main trade-off you're constantly managing there?
You're absolutely right. It is a significant engineering challenge to build and maintain these real-time feature pipelines and tiered caches effectively. The trade-off is clear and constant. More frequent updates for more features mean more compute resources consumed, more data writes to your cache infrastructure, which can become a bottleneck, and generally increased operational complexity and cost. You have to strategically and continuously decide what's worth the cost of keeping hot versus what can be slightly less fresh and kept warm or cold. This decision has to be based on the specific latency requirements of your different fraud detection checkpoints, e.g. login versus checkout versus review queue, and the capabilities and costs of your underlying infrastructure. The ultimate goal is always to get the richest, most up-to-date, and most predictive information to the model precisely when it's needed without breaking the bank or violating critical real-time service level agreements, SLAs. It's all about extracting the maximum signal for the minimum latency tax.
Okay, so now we have these powerful, dynamically updated features coming from our tiered cache. The next step is actually using them. How do we choose the right machine learning models to make sense of all this complex data and actually predict fraud effectively? It really sounds like standard, Off-the-shelf models you might use for other tasks might not always cut it here, given all the unique challenges we've already discussed, the imbalance, the drift, the speed requirements.
You're absolutely right again. Fraud modeling isn't just standard machine learning applied to a new data set. The constraints and objectives are quite different. We need models that are not only highly accurate at finding that rare fraud signal, but also incredibly fast, often needing to return a score in milliseconds. They frequently need to be interpretable, or at least explainable, so analysts can understand and trust their decisions. And they must be exceptionally effective at identifying those rare fraud cases, even when fraudsters are actively trying to look normal, all under strict, real-world operational constraints. Remember, the ultimate goal isn't just getting a high technical score on some metric. It's deploying a model that reliably minimizes real-world financial losses and operational costs, while protecting legitimate users. So when it comes to model selection for fraud, certain families of models tend to shine. Tree-based models, particularly gradient-boosted trees like XGBoost, LightGBM, and CatBoost, are often the top performers in this domain.
Why are they so popular for fraud?
Well, their pros are pretty compelling for this problem. They generally achieve excellent predictive performance, often outperforming simpler models. They handle missing values and categorical variables quite naturally, which reduces the amount of tedious data preprocessing needed. And crucially, they are very good at automatically capturing complex, nonlinear interactions between features like understanding that a certain high click speed combined with a brand new device originating from a shared IP address might be a very strong fraud signal, even if each feature individually isn't that suspicious. They often lead the pack in terms of recall and that critical PRAUC metric we discussed.
Okay, strong performance, handles data well. What are the downsides?
The main cons are that they can be slightly opaque, often seen as black boxes. It can be harder to intuitively understand exactly why they made a specific prediction without using additional explanation tools like SHAP, which we'll talk about later. Also, very large, complex tree models can sometimes be memory-heavy or have slightly higher inference latency compared to simpler models, especially in large-scale, high-throughput streaming environments. They are typically best used when you need that strong predictive power, and you can manage the latency, for instance, in batch processing, or in real-time scenarios where you can achieve sub-100 millisecond inference through careful optimization and hardware choices.
Okay, so tree models are powerful, but maybe a bit complex. What's on the other end of the spectrum?
On the other end, you have good old logistic regression, especially when it's coupled with regularization techniques like L1 or L2 to prevent overfitting and help with feature selection. Its main pros are its undeniable speed, its incredibly fast to train and score, and its high degree of interpretability. With logistic regression, each feature gets a clear, understandable weight or coefficient. This makes it very easy to explain why a particular user or transaction received a certain risk score, for example. You can literally say, this user score increased by 0.5 points because the is-new-device feature was true, and it increased by another 0.8 points because their shared IP account was above 5. This inherent transparency makes it very easy to debug, monitor, and gain trust from analysts and business stakeholders.
Speed and clarity sound great. What are the limitations?
The main cons are that basic logistic regression cannot capture those complex, nonlinear interactions between features automatically the way tree models can. You might need to manually create interaction terms or polynomial features, which adds complexity. It also typically requires careful manual feature scaling, like standardizing inputs, to perform well. Its real sweet spot is when extreme speed and inherent explainability are the absolute paramount requirements, perhaps in ultra-low latency, real-time scoring scenarios where you need a decision in under 50 milliseconds, and being able to clearly articulate the why is non-negotiable.
So it sounds like a classic trade-off, a balancing act between the predictive power of complex models and the speed and interpretability of simpler ones. But I think I've heard about ways to try and get the best of both worlds, something like model distillation. Can you explain how that works in this context?
Ah, yes. You've picked up on a very clever and increasingly popular hybrid approach, using ensembles and distilled models. The core idea here is quite elegant. First, you train a more complex, powerful teacher model offline. This could be a very large, deep XGBoost model, maybe even an ensemble of several models, or potentially even a deep learning neural network with many layers. You train this teacher model using all your available data and computational resources, where time and latency constraints are less of a concern, allowing it to learn the most intricate patterns in your fraud data. Once you have this powerful but potentially slow teacher model, you then distill its knowledge into a much smaller, simpler, and faster student model. This student model might be something inherently quick, like a logistic regression or maybe a very shallow, simple decision tree. The distillation process essentially involves training the student model not just on the original data labels, but also on the predictions or the probabilities generated by the teacher model. The student learns to mimic the teacher's behavior.
So the big smart model teaches the small, fast model how to think.
Exactly. The benefit is immense. You effectively combine the superior predictive power learned by the complex teacher model with the lightning-fast inference speed required for real-time online decisions, all without deploying the computationally heavy teacher model directly into your critical path. It's an ideal strategy when you need that robust offline strength, but absolutely must meet stringent online latency requirements. You get complexity offline, speed online.
That's fascinating. A really clever way to bridge that gap. Okay, so once we've chosen a model architecture, whether it's trees, logistic regression, or a distilled model, how do we actually train it effectively when, as we keep saying, fraud is such a rare event? It still feels like the model would naturally just ignore those tiny fraud signals unless we do something special.
Excellent question, and you're exactly right. It won't learn properly by default. Since fraud datasets are extremely imbalanced, remember that 0.1% to 1% typical fraud rate. Standard model training algorithms will often just learn the easy path, predict not fraud for everything, achieve high overall accuracy, and completely fail at the actual task. This is where specialized imbalanced learning techniques become absolutely essential during the training phase. One very common and often highly effective technique is class weighting. During the model training process, you explicitly assign a much higher weight or cost to misclassifying examples from the rare fraud class. For instance, in libraries like XGBoost or scikit-learn, there's often a parameter like scale pice weight or class weight. You might set this weight based on the ratio of negative to positive samples, effectively telling the model, hey, getting a fraud case wrong is 100 times worse than getting a legitimate case wrong. This forces the model's optimization algorithm to pay significantly more attention to learning the patterns of those rare fraud events, preventing it from just taking the easy way out. It's relatively simple to implement and often works very well. The main caution is that if your few fraud examples are themselves very noisy or contain mislabeled cases, assigning them a very high weight could cause the model to overfit to that noise.
Okay, so weighting makes the model care more about the rare class. What other approaches are there?
Another major set of techniques falls under the umbrella of resampling. This involves altering the data set itself to make it appear more balanced to the model during training. This includes undersampling, where you strategically and usually randomly reduce the number of examples from the majority not fraud class. Imagine you have 999 not fraud examples and only one fraud example. You might randomly discard 900 of the not fraud examples to create a more balanced 99-to-1 or even 1-to-1 ratio for training the model. The obvious risk here is that you might discard valuable information contained in those legitimate examples. A more sophisticated approach, which we touched on briefly before, is SMOTE, Synthetic Minority Oversampling Technique. Instead of just removing majority samples, SMOTE works by creating new artificial examples of the minority fraud class. It looks at existing fraud examples in the feature space and generates new synthetic samples that lie along the lines connecting nearby fraud cases. So if you have two similar fraud cases, SMOTE essentially creates a new, slightly different but hopefully plausible fraud example based on the features of those two neighbors.
So it's like filling in the gaps between known fraud points.
Exactly. It gives the model more diverse examples of the minority class to learn from, rather than just seeing the same few examples over and over again. This can be particularly effective with tree-dosed models. However, it needs careful implementation and tuning. If used too aggressively, SMOT can sometimes create unrealistic or nonsensical synthetic frauds that don't truly represent real-world fraud patterns, potentially confusing the model. And just to mention it, for more advanced scenarios, especially when using deep learning models, which can be very sensitive to imbalance, there's a technique called focal loss. This is a specialized modification to the standard loss function used during training. It dynamically downweights the contribution of easy-to-classify examples. Most of the not fraud cases will likely be easy, and increases the focus on hard-to-classify examples, the borderline fraud cases, and the misclassified legitimate ones. This helps the model concentrate its learning capacity on the truly difficult, ambiguous cases near the decision boundary.
Got it. So, multiple ways to force the model to pay attention to the needle in a haystack. We're explicitly telling the model that missing a fraud is a much bigger deal than a false alarm, so it learns to prioritize catching those rare but critical events. Now, once the model's trained using these techniques, and it outputs a probability score for no transaction, say 0.82 probability of fraud, how do we translate that number into a concrete operational decision? Yes, block this, or no, let it through. You mentioned 0.5 is usually wrong.
Right. That brings us to the absolutely critical step of evaluation and business-aware thresholding. Once your model outputs that probability score, that 0.82 likelihood of fraud you mentioned, you need to apply a decision threshold to convert that continuous probability into a binary classification.
Mhm.
Is this fraud, let's say class 1, or not fraud, class 0? Most people new to machine learning, or those working on problems where the costs of errors are symmetric, might instinctively default to using a 0.5 threshold, meaning anything with a predicted probability above 50% is classified as fraud. But in fraud detection, given the wildly asymmetric costs of false positives versus false negatives that we discussed earlier, using a 0.5 threshold is almost never the optimal strategy from a business perspective.
Why not? If it's more likely than not to be fraud, shouldn't we block it?
Because more likely than not doesn't account for the cost of being wrong. The core idea is that you need to set the threshold based explicitly on the estimated costs and consequences of each type of misclassification, with the goal being to minimize the total expected financial cost to the business, not just maximize some abstract technical metric like accuracy or even F1 score. Remember, not all mistakes are equal in the world of fraud. Let's go back to our nightclub bouncer analogy one last time. Let's say letting in someone underage, a false negative, FN, carries a potential fine of $500 for the club. But turning away a legitimate adult customer, a false positive FP, only results in about $20 of lost drink sales for that person. Given that massive difference in cost, $500 versus $20, would the bouncer only check the ID of someone they thought had a 50% chance of being underage? Absolutely not. They'd likely set their internal suspicion threshold much, much lower. They'd probably check the ID of almost everyone who even remotely looks young, because the cost of making a false negative error is 25 times higher than the cost of a false positive error. They intuitively operate to minimize their total expected loss.
Okay, that makes perfect sense when you frame it with the cost. So how do you calculate that optimal threshold mathematically?
The formula for the expected total cost is actually quite straightforward. Expected total cost, number of false positives x cost per FP, plus number of false negatives x cost per FN. In practice, what you do is this. You take your trained model and apply it to a validation data set where you know the true labels, fraud, not fraud, and you have estimates for your cost of false positive and cost of false negative. Then you iterate through a range of possible decision thresholds, perhaps from 0.01 up to 0.99 in small steps. At each potential threshold, say 0.1, 0.11, 0.2, you calculate how many false positives and false negatives your model would produce on the validation set if you use that threshold. Then you plug those counts into the cost formula using your predefined costs. You calculate the total expected cost for each threshold. The threshold that yields the lowest total expected cost is the one you select as your optimal operational threshold. This business-aware threshold is then used anytime you need to convert the model's raw probability score into a definitive allow, review, or block decision in your live production scoring system. It ensures that the model's actions are directly aligned with minimizing the overall financial impact on the business.
Wow, this completely reframes the goal. Success isn't just about technical accuracy. It's about directly, measurably reducing business losses by being smart and strategic about how you handle the inevitable errors. It's about saving real money. That's a huge shift in perspective from standard ML classification. Okay, we've covered individual behaviors, historical patterns for users, device characteristics, but what happens when fraudsters don't act alone? When they work together? Or when they systematically reuse shared resources like the same few credit cards or IP addresses across many different fake accounts to really scale their attacks. This sounds like a job for something that goes beyond looking at individual data points or single users. Maybe, not graph analysis.
Absolutely. You've hit on a hugely powerful and increasingly critical technique in modern fraud detection. Graph analytics. Fraud, especially sophisticated organized fraud, isn't always committed by individuals acting in isolation. Attackers often operate in coordinated fraud rings or large-scale bot networks. They create multiple accounts that are intricately connected, often through shared infrastructure like those credit cards, IP addresses, email domains, physical addresses, or even device fingerprints you mentioned. Traditional machine learning models, the ones that typically work on tabular data, usually treat each user or each transaction as an isolated row in a spreadsheet. They struggle to see the connections between the rows, but graphs, by their very nature, allow us to explicitly model the entire ecosystem of fraud, revealing these hidden, often complex relationships.
Right, so the core idea is that fraud is often relational and collaborative.
Precisely. Think about some real-world scenarios where this becomes obvious. You might have account farms where literally dozens or even hundreds of fake user accounts are created, perhaps using slightly varied names and addresses, but all linked back to the same handful of stolen credit cards. or the same few burner phone numbers, or a common device fingerprint. These are often set up just to exploit sign-up bonuses or referral programs en masse, or consider shared delivery addresses. Maybe you notice 20 different accounts, seemingly unrelated, all trying to ship high-value goods to the same single, perhaps slightly suspicious commercial mail drop or residential address. Individually, each order might look okay, but the aggregation at the address level screams fraud. You also see rampant IP reuse, especially with data center IPs or compromised residential IPs used as proxies. A single suspicious IP address might be the source of hundreds of small, seemingly unrelated orders placed across many different platforms or user accounts, attempting to fly under velocity check radars. And in large-scale promo abuse, fraudsters might set up incredibly complex referral chains using armies of synthetic identities, all linked together in a network designed to generate endless discounts or payouts.
So instead of just seeing those individual dots on a map, graph analysis allows us to actually see the lines, the connections that link them together. It reveals a much bigger picture of coordinated attacks that would otherwise be hidden. It really is like building that crime network whiteboard you see in detective movies, where suddenly seemingly disparate incidents are revealed to be part of a single, larger conspiracy.
That's a perfect analogy. Traditional tabular machine learning, looking at isolated rows of data, often completely misses these subtle yet absolutely critical structural connections. Graphs, however, are specifically designed to expose shared entities, identify clusters of suspicious activity, and uncover those hidden relationships. This makes graph-based approaches especially powerful for uncovering fraud at scale. They're great at detecting not just the occasional one-off bad user, but entire groups, entire syndicates of coordinated bad actors. It represents a fundamental shift in perspective, moving from an individual transaction or user view to a holistic, interconnected ecosystem view of fraud.
Okay, I'm sold on the why. How do you actually do this? How do you build these graphs for fraud detection?
Good question. The first step is graph construction. A very common and highly effective approach in fraud is to use what are called bipartite graphs. In these types of graphs, you have two distinct types of nodes or entities. Type A nodes might represent your primary entities of interest, like users or accounts. Type B nodes represent the potentially shared resources or attributes, like credit cards, IP addresses, devices, email addresses, or physical shipping addresses. The edges or lines in the graph then represent the interactions or relationships between these nodes. For example, an edge might connect a user node to a card node, signifying user used this card. Another edge might link an account node to an IP address node, meaning account logged in from this IP.
Okay, so you have users on one side, shared things on the other, and lines connecting them based on usage. That seems intuitive. What can you do once you've built this structure?
Once you've constructed this graph, which might contain millions or even billions of nodes and edges for a large platform, you can start analyzing its structure. One powerful technique is identifying connected components. These are essentially subgraphs within your larger graph where every node is reachable from every other node within that component, directly or indirectly. Finding large connected components where many users are linked through just a few shared IPs or devices can be a very strong indicator of a fraud ring or a botnet. It automatically groups potentially colluding accounts together. Additionally, you can calculate various centrality metrics for each node in the graph. These metrics tell you how important or influential a particular node is within the network structure. For example, degree centrality simply measures the number of connections a node has. So, how many distinct users use this specific IP address in the last week? A very high degree for an IP node might indicate it's a shared proxy or part of a botnet infrastructure. Another useful metric is betweenness centrality. This measures how often a node lies on the shortest path between other pairs of nodes in the graph. Nodes with high betweenness centrality act like bridges or hubs, connecting different clusters of activity. Finding a credit card or a device with high betweenness centrality might indicate it's a key resource being used to link disparate parts of a larger fraud operation, making it a critical choke point if you can identify and block it.
This really does feel like building a living, constantly updating map of suspicious connections. It must reveal patterns and insights that are completely invisible if you just look at tables of data.
It truly does. It reveals the hidden topology of fraud. And the next crucial step, once you have this rich graph structure, is to extract graph features for ML models. The core idea here is to translate the structural insights and patterns you've uncovered from the graph into numerical features that your existing machine learning models like XGBoost or logistic regression can understand and learn from. You're basically enriching your tabular data with network context.
Ah, okay. So you're not necessarily replacing the existing models, but feeding them better, smarter features derived from the graph.
Exactly. For a given user or entity, like a card or device, involved in a transaction, you can calculate features derived from its position and connections within the graph. Examples include the node degree, as we discussed, the number of connections it has, shared neighbors count, how many other users share the same device or card as this one, the component size, the size of the entire connected group or cluster that this user belongs to, or maybe a binary feature like eyes articulation point, which flags if removing this specific node would split its connected component into two or more pieces, indicating it might be a critical choke point in a fraud ring. Other examples could be the IP shared count, how many accounts use this IP recently, the average fraud rate of connected nodes, or the entities this user interacts with typically associated with fraud, or even calculating the shortest path distance to known fraudster within the graph network. These graph-derived features are incredibly useful. They enrich your model with vital contextual information about relationships, shared infrastructure, and potential collusion that would be completely invisible if you only looked at isolated data rows for that single transaction. Think about it. A single transaction from a user might look perfectly innocuous based on its own features, but when you add graph features showing that this user is part of a connected component of 50 other accounts, all recently created, all linked by a suspicious IP address cluster, and all using similar device fingerprints, the fraud signal suddenly becomes undeniable.
That's powerful. So we're literally turning the network connections themselves into quantifiable data points that the model can learn from. What kind of tools do people use to do this at scale? Building and querying these massive graphs sounds computationally intensive.
It definitely can be. For smaller data sets or exploratory analysis, standard Python libraries like NetworkX are excellent and easy to work with. However, for large-scale production fraud detection systems dealing with potentially billions of relationships, you typically need specialized graph database technologies and processing frameworks. Tools like Neo4j, TigerGraph, or Amazon Neptune are popular graph databases designed for storing and querying highly connected data efficiently. For processing and feature generation on truly massive graphs, distributed computing frameworks like Apache Spark with its graph frames or GraphS libraries are often employed. These tools allow platforms to build, analyze, and extract features from these vast networks in a reasonable timeframe, enabling them to leverage the hidden relationships that are so often indicative of sophisticated organized fraud.
Okay, so we've got sophisticated models powered by incredibly rich features, including those derived from graph networks. These systems are making decisions, blocking transactions, flagging users for manual review. But as we discussed earlier, these decisions have real-world consequences affecting both the business and the users. It seems like it's not enough for the system to just spit out a score or a decision like fraud detected. We really need to know why it made that decision. This sounds like where explainability comes in.
Absolutely. You've hit on a critically important aspect of operationalizing fraud detection systems. These models don't operate in a vacuum. There's a whole ecosystem of people who rely on their outputs and need to understand their reasoning. Think about the fraud analysts who have to review flagged cases, the operations teams managing the system, the customer support agents dealing with users who are blocked, and even potentially legal and compliance departments who need to audit the system's behavior. For all these stakeholders, understanding why a transaction was flagged or why a user was deemed high risk is crucial. This isn't just about satisfying curiosity. It builds essential trust in the system. It enables effective audits for regulatory purposes, and perhaps most importantly, it's absolutely vital for actually fighting new, evolving fraud patterns by understanding what the system is seeing.
So what exactly do we mean by explainability in the context of fraud ML? Is it about making the model itself simple or something else?
It's less about making the model inherently simple, although simpler models like logistic regression are easier to explain, and more about having techniques and tools that help us understand how even a complex model arrived at a specific decision. It's about translating the model's complex internal logic, which might involve thousands of calculations across hundreds of features, into human understandable reasons. We generally talk about two core types of explainability. First, there are local explanations. These focus on explaining a single individual prediction. For example, why was this specific transaction flagged with a score of 0.9? Tools like SHE values, which we'll discuss, provide this kind of local instance-level explanation. This is absolutely crucial for a fraud analyst who needs to quickly understand and act upon one specific alert. Second, there's global transparency. This aims to provide insights into the overall logic and behavior of the model across many decisions. For example, which features are generally the most important drivers of fraud predictions for this model overall, or which specific hard-coded rules in our hybrid system are triggering most often. This helps data scientists understand the model's general tendencies and helps business stakeholders understand the main risk factors the system is keying on.
Okay, so local explains the why for one case. Global explains the model's general strategy. It really does sound like creating a transparent window into the model's brain, allowing humans to peer inside and understand its reasoning, rather than just blindly accepting a yes-no answer from a black box.
Precisely. And why explainability is so critical in fraud detection really can't be overstated. There are several key reasons. First, as we mentioned, is analyst trust. Human analysts are often the final decision makers, especially for borderline cases sent to manual review. They need to trust the model's reasoning to confidently approve or block transactions. If they don't understand why the model flags something, they might either blindly follow it, which is risky, or more likely ignore it and manually review every single alert from scratch, completely negating the efficiency gains the model was supposed to provide. Explainability empowers them to work with the model effectively.
Right, they need to feel confident in the tool.
Exactly. Second is regulatory compliance. Many sectors, particularly financial services, but increasingly others too, face regulations that require providing reason codes or maintaining auditable explanations for high-stakes decisions, especially adverse ones like blocking payments, closing accounts, or denying services. You need to be able to demonstrate why you took a certain automated action, and vague explanations often don't suffice. Third, it's crucial for fraud-fighting strategy. Explanations help analysts learn about new and emerging attack patterns. By seeing what kinds of transactions or behaviors the model is catching and why it considers them suspicious, analysts can identify novel fraud techniques that they might not have been aware of. This allows them to adapt counter strategies, perhaps by developing new manual rules or suggesting new features to data scientists to explicitly target these emerging threats. And finally, explainability is absolutely essential for creating effective feedback loops. Armed with clear explanations for why a case was flagged, analysts can provide much more informed and specific feedback to the data science team. They can point out when the model's reasoning seems flawed. It flagged this good customer just because they used a VPN, but that's common in their country, or identify new fraud types that the model isn't yet fully understanding. This pattern looks like a new type of refund abuse the model isn't capturing. This feedback is invaluable for iteratively improving the models over time.
That's a great point about the feedback loop. Let me try that analogy again. Think of a fraud decision system like a courtroom. The machine learning model is the judge, delivering a verdict, the fraud score, or the block-a-load decision. But no judge just issues a verdict from thin air without presenting the supporting evidence. The explainability layer acts like the lawyer, clearly presenting the evidence and the arguments, the key features, the triggered rules that led to the judge's conclusion. And the human analyst is like the jury, weighing that evidence to decide what the final action should be. Approve, block, investigate further. Without that lawyer clearly presenting the evidence, the jury can't do its job effectively or confidently. It really highlights how explainability is about empowering a human element in the process, not trying to replace it entirely.
That's a perfect analogy. It captures the relationship beautifully. So given how important it is, how do we actually make these fraud decisions explainable, especially when using complex models like XGBoost? Well, one of the most powerful and widely adopted techniques in recent years is using SHP, Shapley Additive Explanations. SHAP is a game theory-based approach that provides a consistent and theoretically sound way to attribute the model's prediction for a specific instance back to its input features. Essentially, for any given prediction, SHAP calculates a value for each feature, indicating how much that feature's specific value for that transaction pushed the final prediction score up, indicating increased risk, or down, indicating decreased risk, compared to a baseline expectation.
So it breaks down the final score into contributions from each input feature.
Exactly. For instance, a SHAP explanation might tell an analyst the predicted fraud probability of 0.9 for this transaction was driven primarily by new device, plus 0.3 contribution, high transaction amount for Roser, plus 0.25, IP shared with known fraudster, plus 0.2, while long Oster history actually decreased the score, netable 0.1. This gives a very clear quantitative breakdown of the main drivers for that specific decision. SHAP values can be calculated for individual transactions in real time or used to generate explanations for a batch of decisions offline for auditing or analysis. Beyond sophisticated methods like SAP, there are simpler but still valuable approaches. If you're using a hybrid system that combines hard-coded rules with a machine learning model, it's crucial to show which specific rules were triggered. Logging a clear, human-readable reason like flagged because, Rule 17, new device plus large order amount, and Rule 23, shared IP with recent chargeback, gives an immediate, actionable explanation. It's also common practice to simply highlight the top contributing features for each prediction, even without using SHA. You might just show the top 3 or 5 features that had the most influence on the score. It would be like top risk factors: high velocity, shared card detected, new device fingerprint, and perhaps visualize their impact using a simple bar chart integrated into the analyst's review tool. The ultimate goal here is to design the entire review interface for analysts. This means building intuitive dashboards or case management tools that clearly display not just the model score and the recommended decision, block review approve, but also the SHAP summary or top contributing features, any triggered rules, relevant historical context for the user, and the full action history for that user or related entities. To further enhance this human-in-the-loop system, you should include features like structured reason code logging, where analysts categorize why they ultimately approved or denied a case, analyst feedback buttons. This looks like legitimate activity escalate for digger review override model and block that feed directly back into retraining data or monitoring systems, and ideally, those interactive visual SHAP plots embedded right within their workflow. This ensures that every human action is informed by the model's reasoning, and every valuable human insight is captured to make the entire system smarter over time.
So SHAP and similar techniques provide that specific why behind each fraud alert, allowing analysts to quickly grasp the situation, validate the model's reasoning, and take the appropriate action with confidence. That seems incredibly powerful for building trust and operational efficiency in such a high-stakes environment. Okay, this has been incredibly insightful. We've covered the challenges, the features, the models, the graph analytics, the explainability. It feels like we've designed a really robust fraud detection system. But a great model sitting on a data scientist's laptop isn't actually stopping any fraud, right? It's only useful if it's actually deployed and running reliably in the real world, making decisions 24/7. This is where MLOps or machine learning operations comes in, I assume. Especially in a super high-stakes, real-time environment like fraud detection, getting the deployment right must be a whole new set of challenges.
You've absolutely captured it perfectly. This is the crucial final mile, and frankly, often the most complex and operationally demanding part of the entire process. Building a good model is hard. Keeping it running effectively and adapting it continuously in production is arguably even harder. Fraud detection models, as we've established, must do much more than just perform well on an offline test dataset. They must serve live predictions, often within incredibly tight latency budgets, think milliseconds. They need to continuously learn from new fraud patterns as they emerge, and they must adapt gracefully to the constantly changing behavior of attackers. It's really about building and maintaining a living ML system, one that's resilient, scalable, monitorable, and perpetually learning from its environment.
So when we talk about deployment in MLOps specifically for fraud, what does that actually encompass? What are the key pieces?
It's quite broad. It includes all the systems, tools, and practices required to reliably serve these models in production. That means building robust APIs or integrating with existing systems for real-time scoring, setting up batch jobs for offline scoring, and crucially, ensuring those real-time features we talked about are always available with low latency. It also involves ensuring the predictions coming out of the model are properly calibrated and interpretable or explainable, as we just discussed. It covers the entire life cycle of the model after initial training, handling ongoing learning, scheduling regular retraining, managing model versions, providing safe deployment strategies like shadow mode or canary releases, and implementing robust rollback mechanisms in case a new model deployment causes unexpected problems. And critically, it includes continuously monitoring the model's health, its performance metrics, and detecting that inevitable concept drift before it significantly impacts the business.
And why is this MLOps aspect particularly critical for fraud compared to other ML applications?
It matters so much in fraud because of the unique combination of operational realities we've been discussing. First, the latency requirements are often extreme. Fraud decisions for real-time transactions at checkout or login frequently need to complete in under 300 milliseconds, sometimes even under 100 milliseconds, end-to-end. Any delay impacts user experience and conversion rates. Second, as we've hammered home, concept drift is guaranteed in this adversarial domain. Fraud patterns evolve constantly, sometimes weekly, even daily. A static model deployed without a plan for adaptation will quickly become ineffective. Third, the feedback on actual fraud is often noisy and significantly delayed, those chargebacks taking weeks or months, making it challenging to get clean, timely labels for retraining and evaluation. Fourth, the cost of misclassifications is high and asymmetric, meaning bugs or performance degradations in the deployed model can have immediate, significant financial consequences. And finally, robust MLOps provides the critical framework for safely testing and validating new models, often using techniques like shadow mode deployment, allowing you to compare a new candidate model against the current live champion on real production traffic without actually impacting users or risking service disruption. You simply cannot afford to just flip a switch and hope the new model works better. You need rigorous validation in the live environment.
It really does sound like you're not just building the detection engine, but you have to build the entire pit crew, the real-time fueling system, the sensor array constantly monitoring performance, and the detailed maintenance schedule to keep that engine running optimally 24/7 under intense pressure. Your earlier analogy of a high-frequency radar system seems very fitting.
Exactly. Think of your fraud detection system like that high-frequency radar guarding a vital air traffic control tower. It absolutely must scan constantly, performing real-time predictions for every single incoming flip, transaction, or user action. It needs the capability to recalibrate itself automatically or semi-automatically to stay accurate as new types of threats or interference patterns emerge, model retraining and calibration. It must learn from the signals it receives, feeding new confirmed bogey sightings, confirmed fraud cases, back into the system to improve its future detection capabilities, feedback loops. And crucially, you can never afford to just shut down the airport for maintenance during peak hours. Any updates or deployments of new radar software, new models, must happen seamlessly, often running in parallel or shadow mode first, without disrupting the ongoing critical operations. You are truly building and operating a living ML system that has to breathe, adapt, and perform reliably under extreme conditions. Okay, so let's dive into some of the key operational aspects that make this demanding living system possible. You mentioned online versus batch scoring earlier. Right. The first key consideration is the mode of scoring. Online versus batch. Online scoring, also called real-time inference, is essential for decisions that need to happen synchronously within the user's interaction flow. Think about approving or denying a payment at checkout, allowing or blocking a login attempt, or making an instant decision on a new account application. Here, as we said, sub 300 meters or even sub 100 meters end-to-end latency is often critical. This typically requires using lightweight, highly optimized models, like logistic regression or distilled models, and relying heavily on those fast, real-time feature stores we discussed. Batch scoring, on the other hand, is used for less time-sensitive tasks. This could involve scoring all transactions from the previous day to identify potentially missed fraud for manual review, running risk assessments on the entire user base nightly to find dormant compromised accounts, or providing risk signals for longer-running investigative processes. Here, latency is much less critical. Maybe it takes minutes or even hours to run, allowing the use of more complex models or features like deep graph traversals that would be too slow for real-time use.
So many systems probably use both.
Absolutely. A very common and effective architecture in sophisticated fraud detection platforms is often a two-tier decisioning system. There's usually a fast tier that operates in that sub 100 meters range. It might use a simpler, faster model and rely only on pre-computed hot features from the cache. Its primary job is often to automatically block obvious high-confidence fraud with minimal delay. Then, there's often a slow tier. This might have a looser latency budget, maybe 300 meters or more, or it might even operate asynchronously, returning a decision later. This tier can afford to call more computationally expensive features, perhaps calculating graph features on the fly, run more complex models or ensembles, or execute deep, intricate rule sets. Cases flagged by this slow tier are often routed to a human-in-the-loop review queue or trigger asynchronous actions like sending a verification challenge to the user. This layered approach provides a smart way to balance the need for extreme speed for the majority of low-risk traffic with the ability to apply deeper, more resource-intensive analysis for the ambiguous, higher-risk cases.
That layered approach makes a lot of sense. You also emphasized the real-time feature stores and caching earlier. Can you elaborate a bit more on why they are so fundamental to the MLO strategy?
They are absolutely fundamental because, in many real-time fraud detection systems, the bottleneck, the thing that takes the most time, is often not the model inference itself, running the prediction calculation, but rather the computation and retrieval of the features needed by the model. especially those complex historical, relational, or aggregate features we talked about. You simply cannot afford to recalculate things like the user's average transaction amount over the past 90 days, or the number of unique devices this user has connected from in the last 24 hours from raw data every single time a transaction request comes in, especially if you need a response in milliseconds. It would involve querying massive data sets and performing complex aggregations on the fly, which is far too slow. The solution, as we discussed, is to pre-compute these features ahead of time. You run background jobs that calculate these features periodically, e.g. every 5 minutes, every hour, for every relevant entity, like every active user ID, every recently seen card hash, every device stowed. These pre-computed feature values are then stored in very fast access, low latency key value stores or in-memory databases, like Redis, DynamoDB Accelerator, or custom in-memory services. When a real-time transaction request arrives, the scoring service doesn't recompute the features. It simply performs an instant lookup in this cache using the relevant IDs, user ID, card hash, etc., to retrieve the needed pre-computed feature values. This allows the system to score transactions in real time, often well under 100 meters, while still leveraging incredibly rich historical and relational features that would be impossible to compute on the fly. These feature caches are then refreshed asynchronously by those background jobs, ensuring the data stays reasonably fresh.
Got it. So the feature store is like a super fast, constantly updated cheat sheet or library that the model can instantly query for any relevant piece of information about the user or entity without having to do the heavy calculation itself every single time. That makes total sense for achieving speed. What about model calibration? You mentioned that briefly.
Yes, model calibration is another subtle but important aspect of MLOps for fraud. The raw probability scores produced by many machine learning models, especially complex ones trained on imbalanced data, often don't perfectly represent the true underlying probabilities. A model might predict a score of 0.8, but in reality, only 60% of transactions scoring 0.8 actually turn out to be fraudulent. We say the model is poorly calibrated. This misalignment can be problematic, especially if you're using those scores directly for business-aware thresholding, which relies on accurate probability estimates, or if you're presenting the scores to analysts as a measure of confidence. If an 80% score doesn't really mean an 80% chance of fraud, it can lead to suboptimal decisions and confusion. The solution is to apply a calibration step after the model produces its raw score, but before it's used for decision-making. Techniques like isotonic regression or plot scaling are commonly used. These methods learn a mapping function based on the model's performance on a validation set, transforming the raw scores into better calibrated probabilities that more accurately reflect the true likelihood of fraud. This ensures that when the system says there's an 80% chance of fraud, it really means approximately 80%, which is crucial for reliable risk assessment and cost-optimal decision-making.
Okay, so calibration fine-tunes the scores to match reality. Now the big one. Keeping the model up to date with that constant concept drift. You mentioned scheduled retraining and feedback loops. How does that whole process typically work in production?
This is really the heart of the living system aspect. To combat concept drift, models absolutely must be regularly updated with fresh data reflecting the latest fraud patterns. This involves setting up a robust automated pipeline with several key integrated components. First is label ingestion. You need a reliable way to continuously collect new confirmed fraud and non-fraud labels from all relevant sources, those delayed chargebacks, the tags applied by manual review analysts, feedback from customer support, maybe even results from downstream investigation processes. Getting these labels back into your system promptly and accurately is foundational. Second, you need a scheduled retraining job. This is typically an automated pipeline that runs on a regular cadence, maybe weekly, maybe monthly, depending on how fast fraud patterns evolve in your specific domain. This job pulls the latest labeled data, often focusing on the most recent period to capture drift, potentially applies sampling or weighting techniques, retrains the chosen model architecture using this fresh data, and evaluates the new model's performance. Third, you need a model registry. This is a central repository where you track all the different versions of your trained models. For each version, you store the model artifact itself, metadata about when it was trained and on what data, its performance metrics on validation sets, the optimal threshold calculated for it, maybe its SHAP explainability artifacts, and its deployment status. This provides crucial lineage auditability and makes it easy to manage and potentially roll back models.
And you mentioned testing new models safely.
Yes. That's where shadow mode deployment, or sometimes A/B testing, comes in. This is absolutely critical for deploying new model versions without risking negative business impact. When a new model is trained and looks promising based on offline evaluation, you don't just replace the old one immediately. Instead, you deploy the new model in shadow mode alongside the currently live champion model. Both models receive the same live production traffic and make predictions. However, only the champion model's decisions are actually used to block transactions or send cases to review. The shadow model's predictions are simply logged and compared against the champion's predictions and eventually against the true outcomes once labels become available. This allows you to rigorously evaluate the new model's performance, stability, and potential business impact on real live traffic over a period of time without any risk. Only if the shadow model consistently proves to be better than the champion do you promote it to become the new live model. Finally, underpinning all of this is continuous drift monitoring. You need automated systems that constantly monitor both the input data distributions and the model's output predictions and performance metrics over time. Are the statistical properties of incoming features, like average transaction amount or distribution of device types, suddenly changing compared to the training data? That's data drift. Is the model's precision, recall, or false positive rate suddenly degrading? That's model drift. Tools and statistical tests like the Kolmogorov-Smirnov KS test or the Population Stability Index PSI are often used to automatically detect these significant shifts. If your monitoring system flags a major drift, it serves as an early warning signal that the fraud landscape has likely changed, and perhaps an urgent model retraining is needed, or maybe even investigation into a completely new type of attack pattern is warranted.
It's truly fascinating how this entire MLOps ecosystem creates a closed loop. The feedback from the real world, the new fraud cases, the analyst decisions, even the changing tactics of the fraudsters themselves directly feeds back into making the system smarter, more accurate, and more resilient over time. It really is a never-ending cycle of detection, learning, adaptation, and redeployment. Hashtag outro. Wow. We have journeyed through the incredibly intricate, high-stakes, and constantly shifting world of digital fraud detection. From really understanding the cunning, adaptive mindset of fraudsters and the fundamental challenges they pose, all the way to designing and deploying these sophisticated self-learning defense systems that incorporate advanced features, powerful models, network analysis, and critical explainability. It's become abundantly clear throughout this deep dive that this isn't just about building static models or writing simple rules. It's truly a dynamic, ongoing, high-tech battle of wits playing out behind the scenes of almost every digital interaction we have.
Indeed. We've seen just how critical it is to not just acknowledge, but to actively embrace those core challenges like class imbalance and concept drift. Success hinges on using tailored metrics that reflect business impact, employing innovative feature engineering that captures subtle signals, selecting machine learning models that are not only powerful but also adaptable and fast, leveraging the crucial insights derived from graph network analysis, and perhaps most importantly, keeping the human analyst firmly in the loop through transparent, explainable AI that builds trust and drives continuous improvement.
And here's where my mind goes now, thinking about the future and maybe getting a bit speculative. The fight against fraud is constantly evolving, right? And AI technology itself is advancing at an absolutely breakneck pace. So what if? What if in the near future, the fraudsters themselves start leveraging advanced AI much more effectively? Not just using basic automation for scaling attacks, but employing sophisticated generative AI for creating hyper-realistic fake identities, generating convincingly human-like interaction patterns, or even developing AI that specifically probes and learns how to bypass detection models, making their malicious actions virtually indistinguishable from legitimate user behavior. How will platforms need to adapt their real-time feature engineering strategies to spot these hyper-realistic fakes? Will our model architectures need to fundamentally change to differentiate between genuine human activity and sophisticated AI-generated normal activity? And how will our MLOps strategies need to evolve to counter an even smarter, potentially AI-driven adversary that learns and adapts at machine speed, maybe even faster than our current retraining cycles allow?
That raises a profoundly important question and a slightly scary one. And building on that, will explainability become even more critical in that future scenario? Will we need systems that can help humans understand not just why our model flags something, but potentially the underlying patterns and tells of the sophisticated AI deception being used against us? And conversely, how will we, as the defenders, need to leverage our own advanced AI, perhaps new ways to stay one step ahead, maybe even turning the capabilities of adversarial AI into their own weaknesses?
It's a lot to think about. This deep dive, drawing from the expertise out there, has hopefully equipped you with a robust understanding of the current state of the art in this complex field of fraud detection. It's a domain where vigilance is absolutely paramount, and continuous innovation isn't just a nice-to-have, it's a fundamental requirement for survival. Keep exploring, keep questioning the assumptions, and stay well informed because the digital landscape and the threats within it never ever stand still. We really hope you've enjoyed this deep dive into the world of fraud detection. Join us next time for more essential insights on another complex topic.